Let us examine the phase diagrams shown in schematic form on the left-hand side of this slide and discover what features, if any, are physically meaningless. Let us specifically examine the slopes dp over dt for the three coexistence curves near the triple point, which is defined by a pressure of 0.006 atmospheres and a temperature of 273.16 Kelvin or 0.01 degrees C for water. Using data given in your book, you can readily calculate the three slopes associated respectively with the solid liquid, liquid vapor, and solid vapor coexistence curves. The standard enthalpy change for the fusion process at 0 degrees C and 1 bar is 6.01 kilojoules per mole. Similarly, we quoted in Chapter 1 a standard enthalpy change for the vaporization process at 0 degrees and 1 bar, or 45.1 kilojoules per mole. This value can be obtained using the cycle method or the Kirchhoff equation with the value reported at 100 degrees Celsius and 1 bar, specifically 40.7 kilojoules per mole, and also using the molar heat capacities for the liquid and vapor phases. Using the fact the enthalpy is a state function, we obtain a value of 51.1 kilojoules per mole for the standard enthalpy change for the sublimation process from the standard fusion and vaporization enthalpies. Using the densities of ice and water near 0 degrees Celsius and the molar mass of water, we can calculate the change in water's molar volume for the fusion process near 0 degrees Celsius and 1 bar and obtain delta fusion V equals minus 1.6 10 to the minus 6 meter cube per mole. With all this data in hand, we calculate the slope of the solid-liquid coexistence curve as dp over dt equals to delta fusion H divided by T times delta fusion V, and obtain dp over dt equal to minus 1.3 times 10 to the power 7 Pascal per Kelvin. We can also calculate the slope of the liquid-vapor coexistence curve as dp over dt equals P times delta vaporization H standard divided by RT squared, and obtain dp over dt equals 44 Pascal per Kelvin. Similarly, we obtain the slope of the solid-vapor coexistence curve as dp over dt equals P times delta sublimation H standard divided by RT squared, and obtain dp over dt equals 50 Pascal per Kelvin. We conclude from these calculations that the slope dp over dt for the solid-vapor coexistence curve should be slightly larger than that for the liquid-vapor coexistence curve. However, both these slopes should be much smaller, over 1,000,000 times smaller, as a matter of fact, than that of the solid-liquid coexistence curve. This is clearly misrepresented on these phase diagrams. We conclude this lecture by a brief return to the phase diagram of water. Focusing first on the complete phase diagrams on the left-hand side of the slide, we note that it is more complicated than what you were left to believe. First, there are at least 11 different solid phases of water, implying that water molecules can order themselves in 3 dimensions by forming different kinds of hydrogen bonds. Unless the pressure is extremely high, ice 1 is the most commonly observed crystalline form of water. At high pressures, other crystalline forms of water exist. Please note that in this diagram, the slope of the solid vapor and liquid vapor coexistence curves are very similar. On the right-hand side, we have a magnification of the part of the phase diagram dealing with the melting process. we note that the triple point temperature differs from the normal melting temperature by only 0.01 degrees Celsius, and that the pressure must reach 120 atmosphere for the melting point of ice to be depressed by 1 degree Celsius. So it is understandable that for most common applications of thermodynamics in the life sciences, we will assume that the melting transition of ice to water is independent of pressure.